In this session, we are going through the first notebook for 3D geospatial computing. This is the notebook opened through VS Code. And here you have to make sure that you're using the right Conda environment or the right Python kernel. If this is not the case, you can choose the right kernel from here. I have so many other kernels, but you probably have one. If this is your first installation, just make sure that you are calling the right kernel from here. And it's probably a good idea also to activate the right kernel from here using Conda. Conda activate Py3D. For me, it's called Py3D. For you, it's probably called something else. And you can check your installation by typing Conda list, which will show you a list of all the libraries that are installed in this environment. My environment is a little bit larger than yours, so it takes a while to print all of them. No module named what? So that was probably not included in the description of the library in the YML file. So you installed your Conda environment using that YML file, right? Okay, so what you need to do is to navigate to this Conda environment from here. Yeah. So if you are in a Conda environment, you will see the name of the environment inside these parentheses. What do you see there? Base or something like that? If this whole thing is not visible, then you can drag this line above and then you will see your command line. And if you don't have a command line, try to insert a command line from here. What do you see now? Do you see base? Do you see this CMD on the right side? What? What is PowerShell? Okay. Then choose this little right triangle from here. Downward triangle. And then choose to add a command prompt and make it default. Sorry, what? Yes. Well, here you get access to Miniconda. Miniconda doesn't have any interface. This is the interface too. Ah, okay. And I hope you all paid attention to the installation process and added Python to your path, right? If not, I'm sorry, you will be in big trouble, but that's a, I hope that this is not the case, but I can help you fix that issue also. That's not impossible to fix. But if your Conda installation is properly done, you should be able to see the name of the Conda environment here. And you should be able to navigate to the right Conda environment like this. Conda activates Py3D. And then while you are inside this environment, you can install whatever is missing. So you said you're missing rasterio. Conda install rasterio. You get the right installation code. Most of these packages are available on the so-called Conda Forge channel. So this is the right way of installing them. So I can type it like this. Yeah. And I will run this, but I have the package already, so it will tell me that it is already installed. But just for the sake of demonstration, I will do it. So we are showing a remedy for dealing with errors that you might get from this cell. If you run this cell and you get an error message saying something like you're missing this library or that library, then you should correct those issues by adding those libraries to your Conda environment in this way. So right now, for me, it's checking whether I have that package installed or not. So, and in front of each of them, we have written what they're going to be used for. So while this is installing, I will explain that. The first one, LastPy, is for basically for parsing or reading .las or .laz point cloud files, which are file formats for storing compressed versions of point clouds with spatial indexing and all that. And then parsing point clouds means being able to read them and put the points inside an array of points for NumPy. Open3D is the main 3D library that we're using. NumPy is basically the basis of everything that we are doing in these two workshops. So effectively, you can consider NumPy as the language in which we're programming. TriMesh is a geometric 3D computing library. Shapely is for 2D vector GIS operations. GeoPandas is the extension of Pandas for working with vector datasets in GIS. And Rasterio is for a Python library for working with raster GIS operations. And the rest, Matplotlib is a library for plotting. And Pickle is a library for packaging data and serializing data into binary formats. It's a very efficient way of transferring data from one notebook to another. Yeah. Yes. Okay, so if this is the first time you're running this and you don't have the right environment, then you should actually try to install the whole environment by using this .3D workbench, this 3D workbench.yml file through Conda. As soon as I get out of this function, I can show you how to do that. Yeah, that's because I was experimenting a long time before starting. Yes. You don't even have the base. Okay, then I'm sorry, you are somehow in trouble. Did you manage to add a command CMD? Yes. Can you communicate with Conda at all? Like, can you type Conda list or Conda env list? What? Okay, I have to check.
But it's still all by itself. So make another environment
So you have Conda environments, but Conda is not accessible to your client. Okay. So we have a little issue somewhere. Maybe I can help with that issue. The issue is that for one of the students, the Conda environments do not appear in the terminal. So let's check for that. Stack Overflow Conda VS Code Conda not accessible. Conda environment not showing up in VS Code. So let's see what is the fix recommended for this. Okay, can you do this? Control Shift P. And type Python, select interpreter. And can you choose the right Conda environment? Yes. Okay, but can you choose any of them? So let's do it like this. Python select interpreter. You can do this. And what do you see? Okay, so you see a list. Can you use one of them for the sake of the example? Are there different installations of Python or? And then, so for me, it's the one that I've already chosen, but and you have a Python file, and do you have these extensions of VS Code for Python? Yeah, it should be installed for you. Yes. Okay. And try to create a Conda environment. Let's see.
The task environment after you saving with one.
Okay. How do you do that?
The garbage bin,
Sorry, what?
the garbage bin item, the terminal.
Which icon?
Maybe you should click on the three dots. The three dot. Yeah.
Which three dots? This one. This one? Yeah. Clear terminal. Okay. Some more.
Run beside the item. When you go to CM, on CMD or Conda,
Yes.
there is a garbage bin.
Ah, yeah. You can. Ah, yes. You can kill a terminal and start a new terminal. Does that help? And start a new one from here. Does it do the job? Okay. Does anyone else have a similar issue? It was solved. So now you see the base environment and you see another environment. Okay.
Correct.
Yes, but.
And then I what I made in you.
You create an environment and Miniconda to come in the list.
Yeah.
Okay, so for creating the environment, I will search conda create environment from YML. That's the method to do this. This conda cheat sheet is very useful. You can probably keep it, but it might miss the method that I need here. Okay, anyway. Yeah, I know the method, but I want to show you how I search. So create, env create, environment create from file. And this is where you give it the name of the file. Yeah, and to give it the name of the file, you should pay attention to this. Either the file is inside the same environment as your notebook, or it's in a different environment. So in this case, this is one step higher in the hierarchy of files. So the best way to do it is to copy relative path and bring this one as the name of the file. Yeah. So that will be conda and create f. This is the relative path. Yeah. I won't do it because I have already so many conda environments and this will take a long time. But if you don't have the conda environment, this is the command that you should run. Yes, and we should probably also update our environment description file, the YML file, because at least one of the libraries apparently was not included. The rasterio was not included, right? You had to install rasterio manually. Yes. Okay. It hasn't succeeded yet? It hasn't succeeded yet in installing. Okay. Apparently, we had forgotten to put the rasterio library in the YML file. So if you're also seeing an error saying that the rasterio is missing or whatever, then you should install rasterio separately. And for doing that, I was showing you that you should go online and bring one of these methods for conda to install rasterio. I have it, so I won't run it again, but if you don't have it, you have to run this. Okay. In the meantime, is there any question from online participants? Is everything okay with your installations? Shubham, Elnas?
Yes, I think everything is okay.
Okay, perfect.
I'm following it. I'm pretty new to Python, so
Okay,
I'm but I'm here. I'm looking at things. I understand few things, but a lot of things. I mean,
okay,
I'm not really a coder, but and I
okay,
have been learning Python on and off, so I'm just following it online.
okay. No worries, take your time. So, where were we? Okay. So can you raise your hand if you have any issue with running the first notebook so far?
I have created the node and I created it, but still it's free to that some level class. Okay, so it's good. That is not to be solved with projects. What that, I need, I have people, once I get it, but anything like it's like, how do they get it? When I do it, and when I run it, was, first we can like, install it, like. Usually, only on the left side and on the bottom. So you have to install them one by one. From that, yes, by the so you have to be in front of it. And so you initiate a new parameter. Choose the client and next by that. Choose the command. Yeah. Yes. Is I positive? This corner elements. Corner activate option. Okay, now you're ready. And then go online and search for corner install last time. This is to make sure that you can find the right channel. Go to content, first time. Okay, copy the first command which is going to install the channel from the board. Copy it. Anything else? Paste this. So one by one, you should install the okay.
So, I will repeat the question, for the recording. So if you happen to miss any of the libraries listed here and you get an error, then do this. First, go to this little triangle here and start a command line. Navigate to your Python, to your Conda environment if you are not in the right environment. Activate it. Go there and check the list of the things that are installed. Make sure the thing that you want to install is actually missing, and then go and search for it. So imagine LastPy is missing. Conda install LastPy. This simple command should also work in principle, but I usually check it because many of these libraries are actually available through specific channels, mostly Conda Forge. So Conda Forge is a channel on anaconda.org where these libraries are published. And then you copy that command and bring it here. You paste it and then you hit enter and you run it and this will be installed. I won't do it because I have it already installed. Yeah. This is the way to correct your environment. Okay. So I think everybody's.
For me, this is not requested package is already installed, like it is installed, but somehow not accessible, like.
It says it's already installed, so maybe you need to refresh your window. Control-Shift-P. Are you in the using the right interpreter?
Yes. Select the. Control Shift P. Python. Python select interpreter. Actually, the one from workshop. Okay. Yeah, I can do. Now on this again. Take a look on this. Not sure for you want to use one. Try this conversion again. Can I do that? I think majority of those libraries in my another pipeline one daughter. First, can I just do that previous process and just reuse it? My site is not. Yeah. But I already have all of these paid files, so I have backlog report, but I don't have these screens. So I can have make it that other environment can be. It's not instead of this I should need it and if you can open the Python. I don't use Python myself, so you will be on your own on that side. No, I do, okay. I just.
Maybe contact directly and I'll call the environment.
Interesting.
Then you give the recommendation for it, like, but you- I will written environment, so I'm- Change the environment to this.
Okay, but in the long run, you should resolve this issue and you should have access to only one command function. Can you run everything like command list?
It says content not written.
I've had this issue and I've resolved it, but I don't know what is the example. So we will look into it like. If it's not working for you, it's ensure that you're sitting next to someone for whom it's working. That's when I want you to see the prints and stuff.
Okay, so you can maybe start running the cells one by one and see what's happening. We have put a lot of comments, so it should be self-explanatory what's going on here. The first one relates to what we were talking about in the morning in terms of data models. This last.las file is actually kind of a zipped file which contains all the points, probably compressed in terms of using spatial indexing that I explained in the previous session. And the data is not really a simple list of primitives here. So it is probably even serialized and converted into a binary format. So we don't know how it is written. To parse it or to read the data in terms of primitives, we need a parser or a reader, which is the lastPy library here. That's why we are using the lastPy library. And it reads this for us as some kind of a bunch of NumPy arrays. And to put these arrays in the right shape, we stack them together, and we also realize that we need to transpose the array, which is like changing the columns and rows, but in a special way. And we do all these things because we know that the other library, which is Open3D, expects the point cloud to be in a certain shape and format. The shape that it expects the point clouds to be in is an array of points in the form of n by 3. So n points, 3 columns, right? So we bring the points into that shape, the point data into that shape, and then we feed it into the Open3D library. And after running the next cell, you should be able to see this in a separate window. I probably didn't run this, or didn't run this even. Now. Okay. And I should probably be getting it in a separate window, which is something that we can navigate through. This is our point cloud, and while this is running, you see this little wheel circulating, which means that this is running the code. So it's actually taking some computational power from your system. So if you're done with seeing it, you can stop it, and then it will stop. Okay. Any questions so far? No? Yeah? If you can help Aratana with installing the. So the next one is about let me see. Okay, while doing this, we realized that the scale of the point cloud was wrong, so we changed the scale by dividing all the points by 1000. They were written in millimeters. And then why did we do that? Okay, and then from this new array of points which are which is scaled, we computed the minimum and the maximum using two NumPy functions. This is very important. This is kind of the beginning of our adventures with NumPy. What is happening is that NumPy can process an array of things in the same way that Python can process one single thing. So this NumPy function processes the whole array in one go, right? But finding the minimum of an array can be a little bit ambiguous if we don't mention through which axis, because an array has multiple axes. It might have 2 axes or 3 axes or whatever. It is a multi-dimensional array. So here we are specifying on which axis we want to search for a minimum or maximum. And this is a pretty efficient operation if you think about it, because we have so many points, millions of points, and this is happening at the in a very efficient manner. So the axis equal to 0 actually refers to the columns. So contrary to what you might think in terms of the rows being the first axis and the columns being the second axis, it's actually the other way around, because the first axis that will be created when you make an array in NumPy is the columns axis, right? So axis equals 0 means search through columns, okay? So you get the minimum through the columns and to maximum through the columns, and you make minimum bound and maximum bound. And can you guess what is the shape of minimum bound and maximum bound? The array of points is n by 3, right? So if you get a minimum or maximum of that array, we can actually check it. Print min_b.shape. 3 by nothing actually means 3 by 1. If you want it explicitly to be 3 by 1, you can reshape it to 3 by 1. But this 3 by nothing is actually an ordinary array, a one-dimensional array of 3 by 1, because the default is that you have a columnar array. So if nothing is mentioned, it's actually 1, right? Yes, but sometimes you need to also make sure that this is explicitly 3 by 1. In that case, you need to reshape to 3 by 1. So, and again, the thing that is happening here is that this negative or this subtraction operation is actually done using NumPy. This is not possible between two tuples of numbers in Python. The whole reason we can do this in one go is that we are using NumPy. So we are effectively programming in NumPy from now on, right? So two three-dimensional arrays are being subtracted from each other, and the result is also going to be three-dimensional. Diagonal is also a three-dimensional vector. Yes? And the bounding box here is formulated basically as a tuple of two three-dimensional arrays. That's all there is to it. And when it is printed, you see that it's a tuple of two NumPy arrays. This is the bounding box. Okay. And the rest of the process, the most, let's say, sophisticated part of this notebook is this process of pixelization or voxelization in 2 dimensions. which is explained in these two papers. So you can open these two papers separately and read them. But it's basically very similar to the process of voxelization that I explained to you in the previous workshop. So let's go through it step by step. So there's a pixel size as a vector, which is given as a NumPy array. And here we put the size in X and the size in Y, 5 by 5 meters, right? So we create a NumPy array out of this. If we don't put a NumPy array around it, this will be a list in Python, right? But since we are doing everything in NumPy, we have to convert it explicitly to a NumPy array. And then the bounding box in R squared or R2 is formed from the minimum and maximum bounds. But the 0th and the first, or the first and second coordinates, because we want this bounding box to be two-dimensional, so we only take the X and Y coordinates of the bounding box. The bounding box was this tuple that we formed above, right? And now you see that we are already using indexing because these objects are arrays, they have indices. Items in the arrays have indices. And then we form this two-dimensional bounding box again as a tuple of two NumPy arrays. Okay, so far, so good. And then I'm making this bounding box in n squared. Can you see why I'm doing this? For the same reason that we made a bounding box in n cubed for voxelization, we are doing the same thing here to figure out how many pixels we will have, right? And for doing this, we are actually, again, relying on NumPy. This division of two arrays is a pretty mind-blowing operation, actually. We are here signaling NumPy to do an element-wise division of two arrays, even though their sizes are different. That's a good question. I think we are doing that anyway. Maybe we should. Actually, we have done it also below. Yes, here we are doing it. Yeah. Yeah, good question. So we first divide it by the pixel size. So imagine what's happening here. This is actually an array which is of size 4 by 2, right? But pixel size is a 2 by 1 array. So the sizes are not compatible, but they are said to be broadcastable. Broadcasting is something that is always happening in NumPy. If two arrays are broadcastable, that means one can be somehow enumerated in terms of the other. Then these operations can be performed because it is pretty obvious what we want to happen here, right? We want every row of this array to be divided by the other array, right? So that means that the two arrays are broadcastable. So this happens just by typing the slash for division. But this division is actually an element-wise or Hadamard sure division of two arrays that is performed by virtue of this NumPy broadcasting. Yeah. So after a while, this becomes natural to you when you start thinking in NumPy. You start thinking about array dimensions and whether they're broadcastable. If this the operation that you want to do is logical, then you should think about broadcastability, right? And then if it is possible, then it will be done using NumPy in one direction or the other. And here we are updating this data container, the bounding box in n squared, by using another function of NumPy, round to the nearest integer, or rint, this one. And the result of this function is actually an array of floats. To explicitly say that we want them as integers, we are casting the result into an array of integers. And then we have our bounding box in n squared, which is giving us the number of pixels that we will get in x and y directions. Yes? Can you imagine what is happening here? We are dividing by the pixel size, the actual size in R squared. Then it gives us some numbers like this, 51,000 something something. But we have some decimal points. After rounding to the nearest integers, we get rid of these decimal points and we get the total number of pixels that actually fit inside that area, that bounding box. Yeah. And the actual extents of that whole area are much bigger, like 5 times bigger, because the pixel size is 5 by 5. So these are the actual extents in meters, right? So it should be pretty obvious what is happening here right now. And then we form, we use this diagonal of this bounding box, which is a vector that is constructed by subtracting the minimum of this bounding box from its maximum. We construct a tuple of m and n because we need them for enumeration of the two nested loops using which we want to create the pixels. Very similar to the voxelization method. Yeah. Okay, so now we have m and n, and now we are going to get into the loop for making pixels. We first create a bunch of containers to contain what we are going to create, which is an array of pixels in R squared, an array of pixel polygons. Maybe this one is not strictly necessary, but we did it for visualization purposes anyway. And we are creating an array of pixels in R cubed or R3. Why do you think we need them? Pixels in R3? Because we want to put them at the height, the average height of the whole bunch of points that fall into that pixel. And later we want to use these points, which are raised to the set to that height. We want to use them to create a mesh from our point cloud. Yeah. Or from our pixels, let's say. So let's go through this step by step. And we call these kind of pixels in R3, we call them DEM vertices or digital elevation model vertices, because that's the kind of mesh we want to create afterwards. Yeah. You probably know these kind of meshes as TINs or triangulated irregular networks, right? That's the kind of thing we are going to create from these pixel points. So for I in range of m and for j in range of n, this should be pretty obvious why we are doing this, right? We are creating a grid of pixels, so with two nested loops. The pixel itself is again just a tuple of I and j. Yeah. So if you want to spatially index it, you should create a Morton code for this I and j tuple. That should be straightforward. And the pixel in R squared, after you index them with the Morton code of this I and j, then you can use the Morton code to create keys in a dictionary, and then you put only the pixels that exist. Yeah. So if you want to pixelate an object that does not result in the full grid of pixels, that would be the method I would recommend, to only write down the pixels that actually exist, not every other pixel. Yeah, because that takes a lot of space, and spatial indices are globally unique, so you don't have to create all of the pixels to refer to the whole image. You can just write the ones that actually exist. Yeah. Good question. Okay, so, and in the next line, it should be again very clear as to what is happening. The bounding box in R squared, the 0th item, that gets us the minimum corner of the bounding box, right? That actually gives us the pivot point or the origin of that coordinate reference system from which we embed the points in that R squared space. Exactly similar to the method that I showed you in the first lecture in the morning. On that plane, on that oriented plane, we needed a P0. This is that P0 again. In voxelization, we needed the same thing. In pixelization, we need the same thing. Otherwise, our points will be somewhere in the middle of nowhere, right? And the next thing in parentheses, this one, what is happening here? This is the NumPy equivalent of what I did in voxels. So these are two arrays actually. It's pixel n squared is an array, I and j. Pixel size is an array, 5 and 5, a few lines above. So these two multiplied together actually gives us a NumPy array 2 by 1. Yeah, because those two arrays are both 2 by 1. And they're multiplied together element-wise again. So this is again a Hadamard multiplication of two arrays for which we use the asterisks in NumPy. So this is kind of meaningless in Python, but in NumPy this means the element-wise multiplication of two arrays, right? 1 by 1. And the result is going to be an array of the same size. Yes? And then now we have this pixel in R squared, embedded in R squared. So this is actually the pixel point, the points that represents that pixel in R squared. The pixel itself is just a tuple I and j. This is the representation of that pixel in R squared, and then we append it to the list of pixels. And then we make something called a half diagonal. I don't know why we did this. Did we use this? Oh, yes. Yes, so we are making this little vector, we call it half diagonal because it's half of the diagonal of one of these pixels, because we want to use it to create two other points, the pixel bounding box bottom left corner and the pixel bounding box top right corner, these two. The reason we are doing this is the following, that we need to create a bounding box for every pixel, because we need that bounding box. We figured out that we need that kind of bounding box to create an object that is called an axis aligned bounding box in the library Open3D, because this library needed that kind of an object to clip the points in the point cloud into that bounding box here. So first we try to do it with Shapely, because Shapely is also a library that allows you to check whether a point is inside a polygon and so on. But then we realized that it's going to take a long time to do this. And Open3D already had a method implemented to do this, to clip a very large point cloud with a bounding box. So we figured that that would be the most efficient way of doing this. And then we did it. So we did all these things to create this little so-called axis aligned bounding box. And how did we realize that we needed that? We went to the documentation of this crop method of Open3D. This is an object in the Open3D library, in the format of the Open3D library. And we checked the online documentation. We realized that there is a crop method, and that crop method needs another kind of an object, which had to be a very specific thing called an axis aligned bounding box. And we realized that it could be created from 2 points, or a bunch of points. And to make sure that we can explicitly create this bounding box in a correct way, we figured that we can create it from the minimum corner and the maximum corner, or the bottom left corner and the top right corner, right? So this is the whole story of these few lines of code. Yeah. So then the bounding box is created, and then we clip the point cloud into this bounding box, and then guess what we get? We get a NumPy array of points, which is much smaller than the big point cloud with millions of points. This is probably thousands of points, right? Inside one of these pixels, or hundreds of points. And then we change it explicitly into a NumPy array, because we want to use another functionality from NumPy, which is this NumPy average, to get the average height of these points. Imagine now we have clipped the point cloud into the whole polygon that equals the pixel. And now we want to get the average height of this bunch of points and attribute it to one pixel point in the center of this bounding box. Yeah, because we're simplifying the data. Yes. So some of these pixels actually don't contain any point because of the way we have clipped the data. Ivan has clipped the data with a polygon around the city center of Enschede. So some of these pixels actually don't have any points in the point cloud. So that's why we check if the point cloud array that we are getting after clipping the point cloud actually has any points in it. If it doesn't have any points, we don't bother with this operation, otherwise it will fail, right? So this is the little conditional statement. This is what the conditional statement does. And then again, we use the magic of NumPy to find the average point in that whole bunch. The average point is basically the average of this array in one of the through one of the axes of the array. Again, our points are ordered in columns of x, y, z. So if we just average the coordinates through x, y, z axes, then we get the average point. And what is this 2 for? We get the average point. Now, what is 2? Yes, the height is on the third column, which is index 2. That's a z. Yeah, exactly. So 2 is the index of the z coordinate of the average point, right? So we only need that one. Why do we need that one only? Because the x and y are going to be the center of the pixel, right? That is going to be the representative point. Yes? And we already have them. So now we're going to create this pixel point in 3D with the pixel coordinates that we have already in R squared. Yes? And this new average height, right? Something may look a little bit strange here. Let me see if I can. Is this big enough? Do you see this little asterisk here? What this does is actually expanding this array into its constituent elements. So expanding, sorry, this tuple into its constituent elements. This is so far a tuple of two things. And when you put an asterisk before this tuple, it actually decomposes it into its elements. Yeah? Is that clear? We want the x and the y coordinate of this point, pixel point in R squared, to be separately written with commas, with a comma in between them. And this is what the asterisk operator does. This decomposes the tuple into the constituent elements. And then the third element of the array is going to be the average height. And then out of the three of them, we form a NumPy array, which becomes the pixel point in 3D. So now it is, if you look at it from above, you see that the center of the pixel, and it is placed at the average height of all the points that fall into that pixel, right? And we append that to the list of DEM vertices or the digital elevation model vertices. Okay, now it gets a little bit more interesting. So if we visualize this array of as a height map, we also make a height map with indexes I and j with the average height. That is more or less in the shape that we want it to be as a digital surface model or a DSM, right? And the only issue was that when we visualize this array in as a geotiff, it's a few cells down. When we made it as a geotiff and we visualized it in QGIS, we realized that the whole thing is transposed. So we did this transposition here to change I and J to make this proper. And we can already visualize it with the help of matplotlib. This is coming from matplotlib. It's a NumPy array, so we can visualize it pretty quickly like this. And it looks okay as a pixelated digital surface model representation of the point cloud. So you can see that the point cloud is actually different from a digital surface model, right? You know that. The digital surface model is supposed to be regular and pixelated, and every pixel logically represents the average height of the points in that. So it's a depth image, right? In that point cloud. And let me see. Okay, there are a few cells here that are just to represent the pixels in R squared and make sure that when we visualize them, we see a regular grid. So let me run them. Yeah, I actually didn't run this. I didn't run this either. I haven't been running them. Okay, this one first, this one second. Okay, this takes a while. This is a very heavy operation. You have to imagine what's happening here. We are clipping a point cloud with millions of points into quite a few pixels, taking the averages of those points in those pixels, and this takes a while, but it's relatively fast thanks to Open3D and NumPy. Okay, not bad. This is visualized and okay. Okay, we are explicitly putting the points into a particular shape for a two-dimensional array, M and N, and then we visualize them using Open3D to make sure that we get a regular array of points, pixel points in 2D. Nothing very exciting about it, okay, but it was necessary to make sure everything is correct. And then here we are checking the geographical extents of the data. Again, using this asterisk function that decomposes tuples into 2 items. Compare this with this one. The asterisk actually decomposes this into 2 items. And we are doing this because we need these extents to be exactly in this shape for one other operation. Okay, and here we are exporting this data, which the height map data, specifically into a geotiff. And for that, we use GDAL, and GDAL is already imported together with GeoPandas, isn't it? While installing GeoPandas, you're also actually implicitly installing GDAL. And we have imported GDAL also separately from here, from one of the namespaces here. And basically, it's the same data set that we have as a NumPy array. We are putting it into the right kind of data model for being a geotiff. So after this is a proper geotiff that has the metadata and everything, and you can check those things. It has a, here we're putting it into the right coordinate reference system for this code. And something is going wrong here. Okay. And here you can check the metadata. So we're getting these functions, we're getting tips for doing this kind of operations from the documentations of these tools, in this case, Rasterio. This is now a proper raster in the GeoTIFF format, so it can be read by using Rasterio. And when we open it, you can also check the metadata of this raster, and then you see that this is a proper geospatial raster data set that has a CRS, coordinate reference system, EPSG 28992. And the transformation is clear. Everything is known about this raster. And when you visualize it, it essentially looks the same as the height map array that we had visualized above. But with the difference that this is something that you can open now in a GIS application, right? Okay. Okay, so now we want to shift gears and do the next thing, but I need a cup of tea before I'm able to speak any further. So if you want to see what's happening here, where is it? Check this out. Check this one out. This is a very old deck of slides. Actually, not this one. This one. This tutorial is a very old deck of slides that I've published a long time ago. For point cloud processing. On page 41, you see a pseudocode for making a grid mesh out of a bunch of points that are regularly created as a grid. Yeah. So the idea is to form these quadruples of points and refer to their indices and create quadrilateral faces out of these points and write these explicitly as quadrilateral faces. SlideShare is actually trying to sell me my own slides. This is very funny. I have to pay to download my own slides. Anyway, okay, so this is what's happening here. If you want to really understand what is happening here, you should probably draw it. And that's why I've put this drawing here. These points are regularly generated through two nested loops, right? So for m steps, we go in this direction, and for n steps, we go in this direction. But effectively, we are creating a snake like this through the points, right? So when we are adding them to a list, we are essentially adding them with this order, like this. So we know which is which, right? We kind of know which is which. And if you really want to create these quadrilaterals, we can also use this regularity. This is u steps or m steps or whatever number of steps. So this one will be the next point. This one will be the point index for the pivot point plus u steps or m steps. And this one will be the u plus 1 or m plus 1 steps further. So we actually know these 4 points, the indices. And now we can use these indices to form 2 triangles or 1 quadrilateral. But since we are using the trimesh library, we want to create triangles because trimesh can only create triangular meshes. Yeah. And we also want this to be a thin or triangular irregular network. So we create these 2 triangles, but essentially we use the quadrilateral ordering of points. And here I think I've added a little exercise for you to think about a better way of triangulating these squares. A better way to triangulate these squares would mean that you create the triangles using a diagonal line, which is the shorter diagonal line, not the longer one. Is it the longer one or the shorter one? Which one gets you better triangles? Can you imagine why I'm bothering with this? Because these 4 points are not on the same plane, right? So this is not going to be a planar quadrilateral. This is going to be a non-planar quadrilateral. So one of the points is off of the plane, right? So if you want to create good, nice triangles to make the smoothest approximation of the surface, you should triangulate along the shorter diagonal of this quadrilateral, right? So I keep this as a little exercise for you to decide how to change the triangulation if you want, yeah? And you see the effect here, because after we add these vertices and faces to tri-mesh, we have the mesh already. And it's visualized, and you see that it looks nice, but it's also a little bit jagged because of this triangulation being everywhere regular in the same direction. But if you choose the triangle orientation in a smarter way, like choosing to triangulate along the shorter diagonal, the mesh will also look nicer. Yeah. And we are kind of done, which is nice. So here we just put the data of the mesh into a pickle package using the pickle native library. And we also export it into an OBJ file. And we use this pickle dumped mesh in the next workshop for creating a colored mesh with sky view factors attributed to its vertices. Yeah. Okay, so time for questions. So did you manage to run the whole notebook in your system? Yes, everything's running. Okay, perfect. Is it clear? More or less? Okay, so do you have any big doubts, or is there something unclear about the code so far? Nothing, we just we started with 10 by 10, but then it was too coarse, and so we decided to raise it to 5 by 5. Yeah. Actually, it would have been very nice to show you the whole process of developing this. You would learn a lot. You can imagine that many things go wrong when you try to combine so many different libraries, because each of them expects the data to be in a particular format. And you really have to conform to their way of dealing with things, right? But I can summarize those lessons actually into NumPy, because NumPy is the language here, actually. So this was our philosophy all the time, getting the data, breaking it down to the essential components in terms of information content, making NumPy arrays out of it, making sure that the NumPy array is in the good shape or in the right shape or in the acceptable shape for the next library, and then feeding it to the next library. So it's all about NumPy, and also about the documentations of these software applications, the libraries that we're using. The most tricky one is the Open3D, because it expects things to be in very specific shapes, because it has its own data types, which are even not NumPy data types. It has tensors and axis aligned bounding boxes and many namespaces. And you need to develop some hands-on skills by navigating through the documentation of these libraries, and you need to have a good challenge. So we figured with these two challenges, you can get started. But the rest, there's much more to these libraries. But this was to get you started with professional tools for 3D geospatial modeling. Yeah, these are all of the tools that we are using here are the professional tools of geospatial modeling. So in terms of 3D functionalities, they may not be as articulate or broad as a geometric library as that of Rhino. But in terms of being able to deal with geospatial large coordinates and large data sets, they're pretty good. Yeah. Okay. So any question from online participants? I haven't been monitoring the chat. Nope. Okay. So how are we doing with time? I think we are a bit ahead of time. Yeah. So I guess we can just let you explore this code, read it line by line, and ask questions if you want to. Okay, so in the interest of time, I think I can stop the recording if there are no questions from online participants, and we'll see you again in the next lecture.